So there's an issue with finding the points of intersection for polar graphs that we need to discuss. A point can be represented in different ways in a polar coordinate, so you have to take care when you're finding those points of intersection, because of course there's infinitely many representations for every point, but there's also something else going on. So let's consider this example. So I have the circle, which is r equals 1, which I have in this kind of blue ring, and then I have this lovely limaçon with an inner loop, which is r equals 1 minus 2 cosine of theta. Now, if I asked you for the points of intersection of this graph, you would easily say, oh, okay, I can see the points of intersection, no problem. There's one up here, we'll call that A. There's one down here, we'll call that B. But there's also one over here, which we'll call C. Seems straightforward enough. But if you're asked to find what those points are analytically, you might run into a little bit of trouble. Matter of fact, you are going to run into a little bit of trouble. So let's find those points analytically. Oh, and before I go that, what's my period? So I need to know the period for each of these curves. So let me turn off the red one just for the starter. And then let me through this. Okay, so the period for the circle is 2 pi, right? So 6.28, it's done. The period for the limaçon oh, look at that. It's also 2 pi. Okay, so the period for both of them is 2 pi. And again, there's no good way to figure out period other than to graph it and kind of watch it as it goes. So the period for both curves, we'll just make a note. Is 0 to 2 pi. Right? So that's the amount of theta that it takes to get a full circuit for both of those graphs. So it's just something to note. Okay, so if I want to find intersections analytically, that would be setting the two equations equal to each other. I mean, we learned that in pre-calc. You learn, okay, I will let f of theta be equal to, oh, I guess in my case here, I'll color code them. So this is f of theta, right? So f of theta equals g of theta. Okay, so that would mean that 1 minus, let's see, 1 minus 2 cosine of theta is equal to 1. And we would solve this for theta. Okay, well, I would subtract 1 from both sides, so that would get me negative 2 cosine of theta is equal to 0. Divide by negative 2, cosine of theta is equal to 0. All right, so it's easy enough. Theta is equal to 0, right? Oh, it's me. Cosine of theta is equal to 0, sorry. Cosine of theta is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. Now, I'm going to knock these out because they're not within the period. So I'm not going to worry about those. So that got me points of intersection. So the points of intersection are okay, let's see here. 1 comma pi over 2, and then 1 comma 3 pi over 2. Now you may be thinking, well, how did you know it was 1? Well, because I know it's r, and r is 1, right? So the way this goes is r theta, and I have my r already set at 1. So there's my points of intersection, but what points are these on the graph? 1 pi over 2 is A, right? So it's out at the 1 ring and it's a pi over 2. So this is letter A. 1 3 pi over 2 is B. And that's it. That's all that we were able to find analytically. But there's another solution, C. C is right over here, right? So C is a hidden solution. that did not show up in our work, right? C is that third point that's a hidden solution right here, right? It didn't show up in the by hand work that we did. Now, where is that one at? Well, it's at the same place, but it's at different angles. So on the, you can see it when I swing through. So let me show it to you on the graph. Okay, let me put both graphs into play here, and let's see what happens. Okay, so watch the dots. So if I swing through, okay, look at point C, because the blue one's about to get there. Look at that. See that? The blue one's there. See it? So the blue one, the blue curve hits it at pi, right? At pi and 1. But the red curve hits it at -1, because it starts out there at -1, 0, right? With 0 angles when I haven't gone anywhere. So it's the same place, but it hits it at different points in time. And that's why you're not finding it when you do the analytical method. The analytic methods, look, watch. At pi over 2, which is 1.57, look, the two dots, the red dot, blue dot, converge. That's why you're able to find that one analytically. But C, you cannot find because they weren't there at the same angles. We're there at different times. But then if I keep, right there, 3 pi over 2, both the dots intersect. And that's why the analytic method finds that one. And then it goes back, and there we have it. Right? So we could say that it's a hidden solution, and it's at, okay, 1 comma pi, right, for f of theta, or no, g of theta. So for g of theta, it's at 1 pi, but that's equal to, for the other curve, it was -1 comma 0, or if you want -1 comma 2 pi, right, that works as well for f of theta. So it's the same place, but they hit it at different angles, right? They're both that dot over there at C, but they're hitting it at different angle values, right? So it's the same place, C, at different angle values. Right? So analytic methods do not necessarily find all solutions. You have to be super careful and graph everything in Desmos and check, right? Okay, so analytic methods only find ones that are intersecting at the same moment in time. So the analytic method finds A and B, no problem. But C, you're on your own, right? They can find all points of intersection, but they don't necessarily. Check everything, because if the analytic methods are going to fail you, then you want to make sure that you can check everything with a graph in Desmos. The graph obviously showed another solution at C, but you did not find it with your analytic methods. And there was nothing wrong with your analytic methods. It has to do with the fact that they hit that point over here on this graph at different angle values. So the red curve hits it at a different time than the blue curve, or different angle, I should say. Now there's another note to make watch of, which is that so this was note number 1. Note number 1, there's a third point. There can be hidden solutions, right? Hidden solutions are a problem. Note number 2 is that the pole can only be represented by 0 theta, where theta is any angle. So you should check separately for the pole when finding points of intersection. So the pole is r equals 0. And that can happen at all sorts of angles. So you often will just check the pole on its own, right, for points of intersection. And see, hey, did both of those curves go through the pole? Because if they did, they're probably going to be a hidden solution because they're going to hit it at different times. A lot of the time, not all the time, but a lot of the